Barcelona, famed for its endless golden beaches, an unrivaled hub of commerce, culture, sport, and home to one of the world's most iconic buildings. Are you sure this is Barcelona? There's a Punch and Judy stand over there. I'm here in Barcelona to look at some of the maths behind a UNESCO World Heritage Site, one of the most famous buildings in Europe and the instantly recognisable Sagrada Família. I know we're on a tight budget, but that sign quite clearly says Holy Trinity.
I gather they subtitled the whole city for tourist season.
In the austere Passion facade, there's a grid of numbers. It's a magic square, or nearly. A proper 4x4 magic square contains each number from 1 to 16 exactly once. But this one's missing 12 and 16, and it has 10 and 14 twice each. That means instead of adding up to 34, the rows, columns, diagonals, squares, rectangles and corners each add up to 33, supposedly Jesus' age when he died. What they've done here is take a regular 4x4 magic square, and it's a nice one, it's not just the corners and the diagonals that work, there are all sorts of patterns you can play with here. They've taken away one from each of these 4 squares. So I suppose the question is, why those 4? Which other sets of 4 could they adjust without breaking the main properties of a magic square? Which patterns does doing this break? I have to say, I understood the magic square to be carved into the Montjuic sandstone rather than sharpied on a napkin, but I'm sure Senor Subirats knew exactly what he was doing.
Another mathematical artefact of the Sagrada Familia is that the architect, Antoni Gaudí, made great use of ruled surfaces, curved surfaces made up of straight lines. You might be thinking of something like corrugated iron. In one direction it's all wibbly, in the other it's dead flat. And while that is cool, it only drains one way, or if you're unlucky, no ways. Gaudí asked, why must the ends be in phase? So instead of linking the bottom of one curve to the bottom of the other, you link the bottom of one curve to the top of the other. That way you end up with a surface like this, and it drains in both directions. And I think that's lovely, only it's not in the Sagrada Familia. A shape that is in the Sagrada Familia is the hyperboloid, one of my favourite shapes. If you draw straight lines between corresponding points on 2 circles, one above the other, you get a right circular cylinder. But if instead you connect each point on the bottom with a point on the top that's rotated some specified angle around, you get a curving effect on the surface. And that's a really good shape for a deep window. Not because it lets more light through, but because it lets light through more evenly. If your window is a cylinder, you only get even light if it's really shone straight along the axis. With a hyperboloid, you've got much more freedom in where the light can be compared to the window to get the same lighting effect. Throughout the basilica there are catenaries and paraboloids and all sorts of cool mathematical shapes. In classical architecture, you've got 3 basic types of column. You've got smooth cylindrical columns, like you get at the Pantheon in Rome. You've got striated columns, little jaggedy bits all the way around. You get the Parthenon in Athens. And you've got Solomonic columns, which have a twist in the patterns as you go around. You might see those at St. Peter's in the Vatican. And Gaudí said, I'm going to bring in elements of all 3 of those. So we start with a polygon cross section, and I'm going to twist it around a bit, split it, and end up with something that's virtually a circle in the end. So a relatively simple version would look like this. You start with 2 copies of a square in the same place at the bottom of the column. And you're going to rotate one way and the other one the other way as you go up, just very gradually, until in 4 meters time the points of the squares are at the vertices of a regular octagon. Then you make a copy of that octagonal star and twist that in different directions at the same speed. Do that over the next 2 meters, and then you've got a 16-pointed star split again, twist again, the 2-pointed star, 64-pointed star. And it's already pretty hard to distinguish from a circle.
And you do that infinitely many times over the last metre.
Well, Davy was kind of smart about that. He'd generally cover up the last metre or so with something else. Even he wasn't so pernickety that he'd insist on infinitely many bifurcations on the nanometric scale.
But why?
Something to do with being able to include motion and change, it says here.
But surely columns, by their nature, stand still.
Look, I just came here to do some maths. I didn't expect the Spanish Inquisition. I'm not convinced that was Lionel Messi.